Hello friends, good afternoon and welcome to EduSat Live Lectures. Dear friends, as you know that we have started a series on phase equilibria, and today we have brought yet another lecture in the same series for you. In today's lecture, we will try and understand a phase diagram of one component system. To discuss this topic, we have with us our sub-expert Dr. Amit Kumar. Dr. Kumar is Assistant Professor, Department of Chemistry in Dayal Singh College, University of Delhi. Without further ado, I would like to welcome Sir to our studios and request him to start the lecture. Welcome, Sir.
Thank you very much. First of all, I wish very good afternoon to my all dear viewers. Dear viewers, as you are aware, we have been having 4 sections till the point of time in this phase equilibria series, where we had discussed a number of concepts ranging from the component of phase, the component, the concept of phase, the concept of component, the concept of degree of freedom. We had also tried to understand that how we can determine the number of phases, the number of components and the degree of freedom prevailing in a system at equilibrium. It is very important to understand that all these we do talk only about equilibrium systems. Alright, having said this, we also had a derivation of a very important rule called phase rule, and the phase rule is a very general rule which relates all these concepts, the number of phases, the number of components and the degree of freedom which is prevailing in a system at equilibrium. Right. So, now we switch on our attention as an application of Clapeyron equation which we had also derived. We would like to see the phase diagram of water as phase diagram of one component system, how we can understand about this very topic. Before that, we would like to further impress upon one important point, that is called Arnfest classification of phase transitions. According to Arnfest classification, suppose there is a chemical species, any chemical species, which undergo transition from one of its phase to the other phase. For example, if we have a chemical species, then it gets transformed from A, you can say phase A, that is, you can say let this phase A be liquid phase, and B it can be a vapor phase. So, therefore, the transition is that a substance in its liquid phase undergoes transition to solid to vapor phase. Now, this kind of transition is just called vaporization process. This transition occurs during a vaporization process. When a solid transforms to liquid, then 2 phases are in equilibrium, that is solid and liquid, then such a transition is called occurs during fusion process. And when a solid directly converts to vapor phase without turning to liquid phase, then such a transition occurs during the sublimation process. Having said this, now we would like to see how Arnfest have classified these phase transitions and what is the very basis of such a classification. If you remember, when we had discussed the criteria of equilibrium between phases, there we had said that the criteria of equilibrium between criteria for equilibrium between 2 phases is that the chemical potential of a substance in both the phases should be a same value. So, now having said this, it means chemical potential is a continuous function of temperature. We all know that chemical potential is a function of temperature and pressure, and chemical potential of any chemical species increases with increase in temperature and pressure. So, if we have a solid substance and we raise its temperature, then its chemical potential will increase. So, you will have a continuous increase in chemical potential values. Now, it will reach to a particular temperature at which the the substance in solid phase now comes in equilibrium with liquid phase, that temperature called melting point, and at that temperature chemical potential of solid phase and liquid phase will be equal, and therefore at this temperature the two phases, solid phase and liquid phase, will remain in equilibrium with each other till you keep on heating till the whole of solid gets converted to liquid phase. So, what it does mean, and now the rate of increase of chemical potential will again be different with increase in temperature for liquid phase in contrast to that of solid phase. So, it means there will also be a increase in chemical potential for solid phase with temperature and also for liquid phase, but the rate of increase of chemical potential is different for both the phases. And more important is the fact that chemical potential of the solid phase and liquid phase when they exist in equilibrium with each other is the same value. It means if you plot the chemical potential versus temperature curve of a substance, you will notice that there will be a continuous curve of mu versus T curve with one break point with one discontinuous rate of change of chemical potential. Let us have a look at view of the chemical potential versus temperature curve. In that curve you will observe that the chemical potential basically continuously increases. Now we can have a look at this graph where you can see mu is chemical potential. Chemical potential, sorry, it is not an increase but it is a decrease. The chemical potential do decrease with increase in temperature, and for solid phase it do decreases, and the rate of decrease is lesser compared to liquid phase. If it is after the red line, you will observe the liquid phase, for liquid phase the chemical potential also decreases with temperature but decreases at a greater rate, slope is greater. And now it is very important to note that at this red line, the vertical or perpendicular line which has been placed, at this point the chemical potential of solid and liquid phase becomes equal. So, it does mean that chemical potential versus temperature curve of a substance is a chemical potential of a substance is a continuous function of temperature. That is what we mean to say by this point. Now, having said this, chemical potential therefore is a continuous function of temperature. This is one important characteristic. But what about the first derivative of chemical potential with respect to temperature? Let us have a look at this. So, for this if we consider again the transition of a substance from phase A to phase B, then we would like to see the rate of what is the difference between rate of change of chemical potential with temperature at constant pressure for both the phases. So, you can see del mu B, that is by del T, that is rate of change of chemical potential of substance in phase B with respect to change in temperature at constant pressure minus rate of change of chemical potential of the substance in phase A with temperature at constant pressure. So, these are nothing but the first order derivatives of chemical potential with temperature for the two phases. And it is important to note that del mu by del T at constant P is nothing but the negative sign of entropy. So, you have just nothing but negative entropy value of substance in phase B plus positive entropy value of substance in phase A. So, now if whenever a substance undergo transition from phase A to B, this S, the entropy of substance in the two phases, if it is mean the same value, then it should be a 0 value, the net result should be 0. But the fact of matter is that we will observe, we all know that whenever a liquid phase transformed to gas phase or a solid phase transformed to liquid phase from the knowledge of our chemical thermodynamics chapter, that this is a positive value, that entropy of a substance increases when a substance undergo transition from solid phase to liquid phase, or a liquid phase undergo transition to gas phase, or entropy change become a negative value when opposite effect occurs, that is gas transform to liquid or liquid transform to solid. So, therefore, it does mean that now let us consider that rate of change of chemical potential with pressure at constant temperature. Now, similarly we do try to observe the rate of change of chemical potential for the substance in phase B with pressure and also for A. The difference, we will look at the difference between the two rates, that is equal to Vb minus Va, and we all know the Vb and Va is just nothing but molar volume of substance in phase B and phase A, and we all know that gases occupy greater volume compared to liquid and liquid occupy greater volume generally compared to a solid phase. So, therefore, the difference between molar volume of a substance in two phases is different, is a positive value, difference between molar volume is a positive value, and also the difference between molar entropy is also a positive value. So, it does mean that these kind of phase transitions where liquid transforms to gas phase or solid transform to liquid phase or or solid transform to liquid phase or so on, these kind of transitions, by our knowledge of thermodynamics, we get to know that they are accompanied with a change in volume, molar volume, with a change in molar entropy, and accordingly molar entropy according to the first law of thermodynamics at equilibrium transition temperature is equal to negative sign of enthalpy is equal to enthalpy change by temperature, delta H by T. So, therefore, in nutshell we can say that those phase transitions for which are accompanied by a change in molar entropy, in molar enthalpy and molar volume, all these kind of phase transitions are being classified as first order phase transitions. It does mean that if we compare the first order derivative of chemical potential with respect to temperature, the difference between the first order derivatives of chemical potential for two different phases of a substance, this should be a non-zero quantity. What it implies, just have a look at this in the form of a graphical representation. What is the del mu by del P at constant T? Isn't del mu by del T at constant P, that is molar entropy, and you can say negative molar entropy minus S. So, therefore, this is the curve of entropy value versus temperature, that is to say which represents a rate of change of chemical potential, or how the first derivative of chemical potential with respect to temperature varies with temperature, and we all know therefore entropy is a discontinuous function. Whenever this is the entropy change for a liquid, it increases, and when it comes in equilibrium with gas, there is a sudden increase in the entropy value of the system, and again the entropy increases with increase in temperature. So, you can see at one temperature there are two values of entropy. These two values of entropy correspond to entropy of two different phases of a which are present during the transition. So, therefore, entropy is a discontinuous function, and entropy is just nothing but is the first derivative of chemical potential versus with respect to temperature. Similarly, the volume is also a discontinuous function, as a function of temperature. Volume as a function of temperature is a discontinuous function. That is to say, a substance when present in liquid phase, its molar volume increases as the temperature increases, and when it comes in contact in equilibrium with the vapor phase, then vapor phase will have its own molar volume, and therefore, you will observe a discontinuity in the molar volume value at the same temperature, and these two molar volumes do represent the molar volumes of two different phases. And once the transition is complete from liquid to vapor phase, now then again the molar volume of vapor phase again varies. Similarly, enthalpy is also a discontinuous function. So, we can conclude from this discussion is that, concluding point is that those phase transitions which are accompanied by a change in molar volume, molar enthalpy and molar entropy of a substance from one phase to the other, such transitions are called first order transitions, because molar volume, molar entropy and molar enthalpy are just nothing but representative of first derivative of chemical potential with respect to temperature, and hence called first order transitions, because first order derivative of chemical potential represent different values for different phases at same temperature. Coming over to and examples, coming over to examples of these kind of phase transitions is just nothing but the example which correspond to when one solid substance undergo transformation to liquid phase, that during fusion process when some solid substance directly sublimes to vapor phase without converting to liquid phase, that is another phase example of phase transition, and liquid when vaporizes to vapor phase, that is another example of such phase transitions which can be classified as first order phase transitions. And why these are called first order phase transitions, that has already been explained. Right, having said this, now we switch on our attention to second order phase transitions. What we do mean by second order phase transitions? These are also called lambda phase transitions. One point which was forgotten about is very important point about first order phase transitions is that the heat capacity of the substance in two different phases is different. What is heat capacity? Heat capacity is nothing but the heat required to raise the temperature of a substance by 1 degree Celsius. And if we compare the heat capacity of a solid substance, in solid phase, we will see that heat capacity for solid phase of a substance will be much greater compared to the heat capacity for a liquid phase. So, the point is that whenever a solid is heated under condition of constant pressure, then its temperature gets raised and ultimately the temperature reaches a point where the temperature represents the melting point of solid substance at specified external pressure, and this temperature, because this is melting temperature, the solid starts to melt. It comes in equilibrium with liquid phase. So, now two phases are in equilibrium, solid as well as liquid phase, and whatever heat is given now to the system is used up to meet the requirement of lattice energy to convert this solid phase to the liquid phase. So, therefore, although you are heating the system, but you will not observe an increase in temperature so long as two phases remain in equilibrium with each other. It does mean that you are heating the system, you are giving thermal energy, heat to the system, but its temperature does not get raised. Now, coming over to the heat capacity again. Heat capacity is the heat required to raise the temperature of substance by 1 degree Celsius, and at transition temperature, when two phases are in equilibrium, when phase transitions occurs, during that time till the transition is complete, whatever heat you give to the system is not used to raise the temperature, but is used to meet the requirement of lattice energy to bring about phase transition from solid phase to liquid phase. And therefore, you can say that during that time the heat capacity of the substance become infinite. Why I am saying so? Because heat capacity is just nothing but del H by del T at constant P, and del H is a positive quantity for fusion process, and del H is a positive quantity but del T is 0 during phase transition. So, del H is positive quantity in numerator, divide by del T, which is a 0 quantity, which has a magnitude 0, because temperature does not change. So, therefore, dt is 0. So, denominator is 0, numerator is a positive value. So, mathematically we can view that heat capacity, which is del H by del T at constant P, something upon 0 is infinity, so is become infinity. That is, heat capacity is infinite, that is, infinite amount of heat is required to bring about an increase in temperature of the system. Why so? Because so long as solid phase exists in equilibrium with liquid phase, then the phase transition occurs, then the temperature will not change, temperature will remain same. So, during the transition process which undergoes, heat capacity approaches infinity. But it is again important to note that heat capacity is a term for equilibrium state of system, not during irreversible transformation. And here it is important to note that heat capacity was the system was undergoing transformation. System was not in state of in static equilibrium, but was in state of dynamic equilibrium. The system was undergoing transformation, you were heating the system, you were giving thermal energy, heat to the system. System is under the influence of some external agency which supply heat to the system. So, therefore, we cannot say heat capacity is infinite, rather to say it in other words is that we can say heat capacity versus temperature curve, if we look at it, will look like this. We can have a graphical representation, look at the graphical representation of the system. Here you can see the heat capacity rises and then of a system increases with increase in temperature. Now, heat capacity varies here and reaches to a very high value, near infinity, you can say, it keep on increasing. That is how graphical representation you can say about heat capacity, it approaches infinity. And once again, once the phase transition is complete, it ultimately reaches to the heat capacity of that higher temperature stable state. It assumes the heat capacity of that phase which is stable at higher temperature. So, this is very important point to be noted about the heat capacity variation for first order phase transition. Now, coming over to the second order phase transitions, these are also called lambda transitions. It is important to note that first derivative of chemical potential with temperature with pressure is not a discontinuous function of temperature. It is important to note. What it does mean? That whenever such second order phase transitions occur, then they are not accompanied by change in volume, they are not accompanied by change in entropy, they are not accompanied by change in they are not accompanied by change in volume, or they are not accompanied by change in enthalpy, but as well as entropy. But the second order differential of chemical potential is a discontinuous function then. So, since there is the second order differential coefficient of chemical potential with temperature is a discontinuous function, these kind of phase transitions called second order phase transitions. And first order differential coefficient del mu by del T is S. So, for first order phase transitions it means S is a discontinuous function, but for second order transitions S is not a discontinuous function. Entropy of the substance in two different phases will be same if a substance undergo second order phase transitions, or in other words, if the two phases of a substance participate in a second order phase transition, then there will not be a change in entropy of substance in two different phases. There will not be change in volume, there will not be change in enthalpy, but there will be change in rate of change of entropy in one phase, that will be different, and rate of change of entropy with temperature in other phase will be different. That is what will be the main difference. and therefore, second order transitions are the ones which are accompanied by a different rate of change of entropy with temperature and pressure for two different phases which are representative phases during the transition of a substance. And therefore, it now become important to understand which kind of phase transition is this. Is there any example which represents such a phase transition? The answer to this question is order disorder transition in alloys represent the second order phase transitions. Alloy, we all know, is basically composed of different metals being mixed in different proportions. So, such alloys, if there occurs order disorder transition, means different rate of change of entropy, different randomness rate if they assume, then such transitions are called second order phase transitions, because there is no change in molar volume of substance, there is no change in molar enthalpy of substance, there is no change in molar entropy of substance. So, such transitions are called second order phase transitions. Having said this, now we switch on our attention towards the phase diagram of water. Now, it is the representative phase diagram of water at moderate pressures. Why I say moderate pressure? If you look at the diagram, then the pressure varies as we move upward. So, we discuss this phase diagram in our subsequent module. Thank you. Good afternoon, viewers. In this module, we are going to study about the phase diagram of water. So, let us have a first of all look at the representative phase diagram of water. Phase diagram, as we can see over here, represent different regions of stability of different phases of a substance. So, you can see over here we have very many curves over here. This is curve OB over here, then curve OC we have here, and then curve OA we have also here. And now these are the curves OB which separate two different phases, solid at the left hand side, and at the right hand side there is liquid. And below the curve AOC there is vapor phase, Now, this phase diagram is nothing but the pressure versus temperature curve. So, we plot the equilibrium vapor pressure versus the temperature of the system, and we can note that the area to the left of curve BO and above curve OC represent all points, locus of all the points bounded by the curve or which lies in the area to the left of curve BO and above curve OC represent the equilibrium state of system in which there is only presence of a one single phase, that is solid phase. Now similarly we can have a look at this. The area which is represented by the portion which lies to the right of curve BO and above curve AO represent a liquid phase as it is written in the phase diagram, and locus of all the points which lies below the curve AOC, all these points, these represent, each point in this area represent equilibrium state of system where there is only vapor phase. Now let us have an attention towards what these curves BO, OC and OA do represent. The curve BO represent the condition of temperature and pressure, because curve BO is a locus of all the points on the line BO which represent particular temperature. Each point on curve BO represent a particular pressure and temperature at which solid is in equilibrium with liquid phase. Similarly, curve AO represent all the points on curve AO represent the equilibrium state of system where in the system there are two phases in equilibrium which are nothing but liquid and vapor phase. Similarly, curve OC represent the locus of all the points, each point on which represent the equilibrium state of system in which the solid phase and the vapor phase are in equilibrium. So therefore, the regions, solid region represent one phase equilibria points, liquid region, that is another one phase equilibria point, and the vapor phase also represent the region where there are number of point lies where these represent one phase equilibria, that is vapor phase, and all these lines or curves do represent two phase equilibria. For example, curve BO represent solid liquid equilibrium, curve AO represent liquid vapor equilibrium, and curve OC represent solid vapor equilibrium. And now what about this point O? This is the point at which all the three phases, solid, liquid and vapor phase, do exist in equilibrium with each other, and hence because it is the intersection point of all the three curves AO, BO and OC, and all these curves therefore do meet at point O, and therefore point O represent a triple point where the three phases are in equilibrium with each other. Having said this, now we look at the point that phase diagram for water at moderate pressures. Why I have said moderate pressure is because we need to understand, as we keep on raising the pressure, then we will keep on moving up, and upward motion will continue in the graph. Upward movement as continues in the graph, we will observe at high pressure that there are different crystal pattern of water in solid surface, in solid phase comes, and there are 7 different kind of ice which exist depending upon the crystal structure, and is called ice 1, ice 2, ice 3, ice 4, 5 and 7 and so on and so forth. So the point is that all these different crystal pattern of water in solid phase ice occurs at very high pressure. So, therefore, for our syllabi purpose, it is important to note that since in the undergraduate level we have to consider phase diagram of water only in moderate pressure. More important is the fact because we treat water only within pressure range from 1 atmosphere to some higher atmosphere pressure for our experimental purpose only in our laboratory at the undergraduate level. So, it is important to understand the phase diagram of water at moderate pressures. So, that is why this phase diagram which we are discussing over here for water represent the represent the phase diagram of water only at moderate pressures. Now, having said this, we would like to also understand that this phase diagram is in accordance with the phase rule. What is the phase rule equation? If you remember, phase rule equation says the degree of freedom is nothing but is equal to C, the number of components, minus P, the number of phases, plus 2. So, C here the component number of component for when water only is being taken in the system, it represents 1 only. And if we have only gas phase or only liquid phase or only solid phase, then we have only 1 phase in the system. So, 1 component, 1 phase. So, C1 and P1, C minus P plus 2 therefore becomes 1 minus 1 plus 2, which is equal to nothing but is equal to 2. So, degree of freedom is 2 for the system which has only water as chemical component present in the system and has only the presence of a single phase, that is if there is only solid phase, if there is only liquid phase, if there is only vapor phase. What it does mean, what implication this point has? It is important to note that if the degree of freedom for a one phase system is for one component one phase system is 2, it means you can vary either temperature, you can vary both temperature as well as pressure of the system without producing any change in physical state of system. It means solid phase will exist as such in the solid state if you vary the temperature within a given range, or you can vary pressure also within a given range. It means you have 2 degrees of freedom, you can vary temperature, you can vary pressure within a given range. That is important to note, that the point is that within a given range only you can vary temperature, you can vary pressure, such that there is no change in physical state, that is solid state of the system. Similarly, that same theory prevails for the liquid state, liquid phase, and same thing can be talked about the vapor phase. And this point can be seen from phase diagram of water itself. If you look at this, I say this region where solid exists has a number of points. Each point represents the temperature pressure condition at which a solid phase exists. It means you can vary the temperature from this point to this point over a range of temperature till the fusion curve meets, or you can vary the pressure also, external pressure also on the system if you move vertically upward in the phase diagram. So, that means solid phase will exist over a range of temperature, range of pressure, and you can vary the temperature, you can vary the pressure without changing the physical state, that is solid phase of the system. Similarly, in the phase diagram you can see there is a region which represents liquid phase. So, again you can say that there is only one phase, liquid phase, and therefore liquid phase is also stable over a range of temperature and range of pressure. Then that range we should know in order to understand within what temperature range we can vary temperature and we can vary pressure in order that liquid phase remains stable. Similarly, vapor phase also is stable over a range of temperature pressure values. So, therefore, this point is in accordance with the phase rule. Now, coming over to the point, if there are two phases present in equilibrium in the system, or in other words, if we have two phase equilibria in the system, that is, if there is gas in equilibrium with liquid, or if there is gas in equilibrium with solid, or solid is in equilibrium with liquid, then it means you have two phases in equilibrium with each other. The number of phases is 2, component is still 1, that is C equal to 1. So, C equal to 1, P equal to 2. So, therefore, F equal to C minus P plus 2. So, C equal to 1, P is equal to 2. It means 1 minus 2 plus 2, that is equal to 1. So, degree of freedom gets restricted by 1 now. Earlier, when there was one phase, the degree of freedom was 2. When now you have two phases in equilibrium, then you will have only 1 degree of freedom. It means you can vary either temperature or pressure. What implication it has? Let us have a look at this on the phase diagram. Now you can see on the phase diagram, this point E represent one condition of temperature and pressure. Point E represent the temperature T2 and the pressure P1 over here. At point P, pressure is P1 and temperature is T2. Now, if we change the value of temperature, or you can say of pressure from P2, from P1 at point E to P2, then what the system will try to do? It is important to note that the volume of the system is kept constant. Now, what the system will try to do? When the pressure subjected on the system is decreased, now the more and more of liquid will try to vaporize and will try to fill. How the pressure is decreased? If you consider a liquid is in equilibrium with its vapor being confined in a cylinder fitted with movable piston, if you increase volume, now the vapors which are subjected in lesser volume, now the volume is increased, so they are accessible to greater volume. So, therefore, vapor pressure will decrease, which will come in equilibrium with external pressure. That is how pressure on the system is decreased. Now, when the pressure is decreased by way of increase in volume, then how the system will try to cope up with this situation? The point is that liquid will try to vaporize under the influence of lesser pressure by changing increase in volume. So, then the liquid will try to vaporize and will try to the accessible space above it and will again try to reach an equilibrium with the external pressure. So, it will reach the equilibrium, but in order to bring about the same value of pressure, the changed value of pressure, what it needs to do? In order to bring same value of pressure, what it needs to do? It needs to vaporize, and for vaporization process it requires thermal energy. So, from where the heat will come? Heat will come from the system itself, so its temperature will also decrease. So, it means if you change the system, if you change the pressure of the system from P1 to P2 and accordingly the system tries to go from point E to point D, then automatically the system will try to adjust itself by way of vaporization, so that its temperature also gets decreased and ultimately reaches at this point on curve OA. If during this decrease in this achievement, if the whole of liquid is used up and there is no more liquid to vaporize, then the system gets completely transformed from two phase to one phase, and therefore ultimately the system will not be on OA curve, will be lying below to the OA curve. So, what I mean to say is that if you fix the if you tell the one value of temperature, then there will be another value of a fixed value of pressure. If in the system there is two phases in equilibrium, and all these two phases are represented on the curve, either OA if liquid and vapor, on curve BO if solid and liquid, on curve OC if it is solid in equilibrium with vapor phase. Having said this, Now coming over to the triple point. So, therefore, degree of freedom is 1 for 2 phase equilibrium and for the triple point 3 phases in equilibrium. So, C is 1, P is 3 and degree of freedom equal to C minus P plus 2 and C is 1, P is 2. So, 1 minus 2, 1 minus 3 because P is 3 plus 2, that is 3 minus 3 is 0. So, degree of freedom is 0, it means system is invariant. If you want 3 phases in equilibrium with each other, it means you can neither change temperature nor change pressure, you cannot change any variable whatsoever of any kind. That means on this phase diagram, if you see, point O is unique point at which curve BO, AO and OC intersect, meet, in other words we can say. There is no other point and therefore is called triple point and is unique point where 3 phases are in equilibrium and is unique point. You cannot change temperature, you cannot change pressure. If you do so, then the 3 phases will not remain in equilibrium, rather the 3 phase will convert to 2 phase or 1 phase. Right. So, therefore, we have a system, we call system as bivariant if it has 2 degree of freedom, we call system as univariant if it has 1 degree of freedom and we call system as invariant when degree of freedom is 0 or and such degree of freedom is 0 at triple point. So, that triple point lies for the phase diagram of water at point O. Now, having said this, now the point is curve OA is known as vapor pressure curve. Curve BO, because why curve OA is known as vapor pressure curve? Because on this curve vapors are in equilibrium with liquid phase and liquid, in other words we can say, transform to vapor phase. So, therefore, that is the reason OA curve is called vaporous curve or vapor pressure curve. Its upper limit, now the upper limit means the point A. How long this curve can be? This is another question now which can be asked, or in other words, what is the upper limit of the vaporization curve? The upper limit of vaporization curve for any substance is its critical temperature. The critical temperature and critical pressure represent the temperature pressure values at which, above which, critical temperature is the one above which you cannot distinguish between liquid and vapor phase. The distinction between the two is lost. Why it is so? And I would also like to stress upon this point, but before that I would like to state that critical temperature for water exists at 374 degrees Celsius, and in order to understand what this critical temperature means and why it is the limit of OA curve, it is now can be stressed upon by the fact that consider a liquid phase at consider liquid water at 25 degrees Celsius. Now, when it is confined in a closed container or in a closed system, then it will vaporize depending upon the temperature, let us say that is 25 degrees Celsius, and it will, when it will vaporize, it will fill the hollow space above and it will exert the vapors will exert the pressure, that pressure known as at equilibrium state vapor pressure, and when the temperature is raised from 25 degree to 30 degree, more vaporization will occur and there will be greater vapor pressure. As we continuously increase the temperature of system, more and more vapor phase will become richer by the substance, whereas liquid phase layer will get depleted. Why so? Because vaporization is continuously occurring, substance is undergoing transformation continuously from liquid phase to vapor phase. So, the point is that the liquid phase when it is heated, its density gets decreased. Why the density of liquid phase gets decreased is because we all know that because of expansion coefficient, all chemical species with increase in temperature undergo expansion. So, liquid water also undergo the same process. As it is heated, its expansion occurs. So, the amount of substance is same, but now the same amount of substance will occupy greater volume at greater temperature at fixed external pressure. So, it means as you heat the liquid water, its density continuously will decrease. On the other hand, coming over to the vapor phase, as the temperature is raised continuously, more and more of vaporization will occur. So, vapor pressure will increase because more vapors are confined now in the same hollow space. So, therefore, it means the amount of chemical constituents are continuously increasing in vapor phase and continuously decreasing in liquid phase. But the volume of the confined space for the vapor to get an access is the same, but the chemical entities are increasing in the same volume in the vapor phase. It means density of vapor phase will continue to increase. Now, this is important point. When the density of liquid phase continuously decrease and density of vapor phase continuously increase, now can we think of a temperature at which density of liquid phase and water phase is being the same? Why I am saying so? I am not saying that we are heating the system at one external pressure, mind you, because water has boiling point 100 degrees Celsius at 1 atmosphere pressure. You cannot go as continuation of water in liquid phase in equilibrium with vapor phase at 1 atmosphere pressure. You have to continuously change the pressure too. So, therefore, what I mean to say is that as both temperature and pressure changes along curve OA in phase diagram of water, please have a look at the representative phase diagram. Along curve OA, as the temperature continuously increase, along with temperature the pressure also increases. What happens is that the density of liquid phase continuously decreases, the density of vapor phase continuously increases, and ultimately point A is reached where the density of liquid phase and density of vapor phase become equal, and it is that temperature which is called as critical point, where you cannot make a distinction between liquid and vapor phase because both has same densities. That is critical temperature, and therefore, this liquid phase, when we say liquid phase is in equilibrium with with vapor phase, it means there is clear distinction between liquid and vapor phase. So, curve OA continues till point A up to the temperature at which there is a distinction between a liquid and vapor phase, but beyond at a temperature beyond point A, you have a liquid, you cannot make a distinction between liquid phase and vapor phase, and hence you can say it is reached the critical temperature. Now, you cannot, since you cannot make a distinction between liquid and vapor phase, you cannot draw vaporization curve beyond point A. So, point A is the limit to which the vaporization curve can be drawn, and this limit represents the critical temperature of a fluid, of a substance, which in this case for water it exists at 374 degrees Celsius. Right, this is one limit we have discussed for vaporization curve. To the other limit, let us have a look at this. Other limit is point O. So, if suppose you have a cylinder fitted with a movable piston in which liquid water is placed and it is in equilibrium with pressure, suppose point A is that point. If you decrease the temperature of the system continuously, the vapor will continue to condense and will try to form liquid. More and more of liquid will form and vapor pressure will continue to decrease along curve AO. Ultimately, a temperature is reached called triple point temperature, at which now upon condensation the vapor phase will not not transform to liquid phase, but will start transforming to solid phase as well, because they have reached transition temperature represented by point O, which represent the point at which chemical potential of all the three phases, solid, liquid and vapor, become equal. And so therefore, the vapors not only condense to liquid phase, but now they start condensing to solid phase. So therefore, all the three phases at triple point comes in equilibrium, and hence vaporization curve, since is a curve which represent the equilibrium state of system, different equilibrium states of system at which liquid and vapor are in equilibrium, two phase equilibria, and therefore the minimum limit of vaporization curve is triple point, at which solid, liquid and vapor phase all comes in equilibrium. So we have discussed this vaporization curve in today's module of phase diagram of water. In the upcoming module, we will go to discuss about the fusion curve, about the sublimation curve, and we would like to try to see the various implications of this knowledge which we do obtain from phase diagram in terms of physical observations which we make around us. For example, skating on the surface of ice, for example, weathering of rocks, what is the source of water in rivers, and also we would like to see we can cut through the we can insert a knife in a ice cube without cutting it into two pieces. All this knowledge comes from phase diagrams that we will try to see in our upcoming lecture. So stay tuned. Thank you so much.
Dear friends, on that note, we would like to thank Dr. Kumar for coming to our show and delivering a lecture. And thank you, dear friends, for watching our show. Stay tuned and keep watching. Thank you.